ready? Pretty close? Alright, so let's see. Things on my reminder/announcements. 1, mastering is due on Friday, and about 2/3 of you have successfully signed in, so that's good. If you're having troubles, just let me know. I can help out in some way, or at least tell you maybe what the issue was and get you sorted out. And we're going to do a group quiz on Friday. So you may be thinking, gosh, who's in my group? So you can scope them out before Friday. Let's see if I can do that. I'll give everybody a few minutes, and that way everybody can find themselves. I did my best to give everybody at least 1 or 2 people that they know in their group. Some people are obviously more popular than others in here because they were on several people's lists. So I did my best to make everybody happy. Am I missing anybody? Does everybody see their name on the list? Is everybody on the list? Okay. And if you haven't figured out who your 3rd or 4th person is, we'll figure it out. So you can scope them out before Friday at least. Okay. The other piece of housekeeping I have to do is, because it's the first week of class, I have to take attendance. So I'm just going to pass this around just so that I can tell the registrar that yes, you were in class, and yes, you should be charged for taking this class because you were physically here. So I'm just going to pass it around. As long as it gets back to me, just check out your name. Then I have to drop you. So, I mean, that's the other thing. If you don't show up today or Friday, then you get automatically dropped from the class. But then you don't get charged. So there's some trade-offs in there, right? That's right. No class, but you also don't get charged. But I mean, you're in there, right? Alright, I'm still working out some technicalities with the document camera, because the neck is really long, but my paper ends up hanging off the bottom. If I don't do that, then you can see the shoes. So I'm trying to figure out exactly how to have this camera so that you're not seeing just my feet for the entire lecture. I'll be more careful about what shoes I wear. Right? You just keep seeing what's past. It's very distracting. They are sparkly. They're Fergie fur shoes. Oh. Yeah. But you didn't know that Fergie had her own fashion line, but she does. And they are sparkly. So. I also got them at Big Lots. So apparently they're not selling that well because they are on super, super discount. Alright, so chapter 12 is where we're going to take all the stuff we did on Monday, right, about polar, non-polar, hydrogen bonding, all that kind of stuff, and apply it to solutions and how things get dissolved. Alright, so this shelf is where I'll type of solutions. So most of our solution reactions are going to take place between either an ion and a solvent, or a molecule and a solvent. And for just about everything we're going to do this semester, the solvent is going to be water. And a solution, way back when from chapter 1 or 2, right, was a homogeneous mixture of 2 or more substances together in a single phase, where we have the solvent, which is the molecules in the larger amount, and we have the solute, which are the molecules in the smaller amount. Right, so you have some kind of combination of, we'll say, salt and water, right? And so you mostly have water, you add a little bit of salt, so in that case, the salt would be the solute, and water would be the solvent. It's the thing that's dissolving solute. Alright, so the solute is the thing that is being dissolved by the solvent. So you're going to take a look at how intermolecular interactions affect the ability for the solute to dissolve in the solvent. So we're going to take what's called a molecular view of the solution process. Where we're going to look at how liquids and solids interact with themselves and then interact with each other. So, right, I had sodium chloride and water. Alright, so I'm going to be looking at how the sodium interacts with itself, like if I had two sodium molecules. I'm going to look at these interactions. I'm going to look at these interactions, and I'm going to look at these interactions. So in my example over here, the solvent-solvent would be the water interacting with the water. The solvent-solute would be the water and the sodium chloride. And the solute-solute would be the sodium chloride and the sodium chloride. So I'm going to look and see how those interactions change depending on how much I have in there, what the temperature is, and do they mix, right? Do they even have a solvent-solute interaction? So when we dissolve something, there are 3 steps to dissolving or 3 steps to making a solution. They're not necessarily numerical, but these are the 3 things that happen. One of the things that has to happen is the solvent molecules have to move apart in space to make room for these solute molecules, right? They have to separate somehow. The solute molecules have to separate from themselves, and then you have to mix the solvent and the solute. All 3 of those chemical processes have to happen in order to have complete dissolving. So to do these separation steps, actually all 3 of these steps, it's either going to require energy or it's going to give off energy. Alright, so if I have a process that gives off energy, what should the temperature change be then? If it's giving off energy, does it get colder, hotter, or stay the same? It gets hotter. So if it gets hotter, what do we call that in terms of thermodynamics? Right, these are going to be exothermic reactions. So then, if they require energy, they should be what? Endothermic, right? So all 3 of these steps have some sort of energy requirement to them. And so the energy requirement is going to depend on my pen's dying. Okay. It's going to depend on those intermolecular forces. Right, if they're real strong forces keeping the salt as a solid, that's going to be a different energy amount than if the salt is real easy to break apart, which happens to be salt is real easy to break apart. But so depending on how they interact with each other, we're going to be either endothermic or exothermic. That leads us to definition of solubility. So how likely is something to dissolve? Solubility is the measure of the amount of solute that will dissolve in a solvent at a specific temperature. So depending on what things we change, the solubility measures will change, right? So if your solution's hot versus cold, it's different. If you switch from water to motor oil, right, that'll also affect it. So it's a very specific set of parameters that can measure solubility. So let's take a look at some examples. Here we go. Let's say I want to dissolve calcium chloride into water. What is going to happen to the concentration of the individual calcium ions and the individual chloride ions? Alright, so I had calcium chloride solid. Based on this information I just gave you here, is it an ionic compound? There's ions. Yes, right, so it's an ionic compound. They're going to turn into ions. What's missing from my balanced chemical equation? Right, I need two of those. So this is what I had at the start of my reaction, and this is what I have at the end of my reaction. Did I have any ions when I started? No. Do I have ions when I ended? So did it increase or decrease? Increased, right? It seems really obvious. It is. It is. The concentration of these ions must have increased because the solid dissolved. Alright, what if we get to the point, calcium chloride is a tricky thing, so you've probably never actually done that. Let's say you are making Kool-Aid. People still make Kool-Aid, right? Maybe your powdered Gatorade, something like that. And you have the kind where you have to add the scoops, right? It's not just a packet that's exactly measured out. So you're going to do the scoops into a pitcher, right? So you add one scoop and you stir it up and you're like, it's like pale orange. So you're going to add another scoop, right? And a little darker. You add the third scoop, dark orange. You go ahead and you add the fourth scoop and stuff starts to, like solids at the bottom. What is that stuff? Right, it's Kool-Aid, right? It's no longer dissolving. You have passed the point that all the Kool-Aid can dissolve. You have made what's called a saturated solution. It's where you have put in all the solid that can possibly dissolve, plus a little bit more. Right, so saturated is where you're at the maximum amount. Right, the maximum amount. You're right at that precipice of being too much. Exactly right. So saturated is the maximum amount. When we get to the point of supersaturated, that is a solution where more than the maximum is dissolved. When we reach this point of saturated, we are at what's called an equilibrium in solution. And we can think about it in terms of, well, what's the best way to draw that? So I'll say this equation is not saturated, right? Because the arrow is indicating that I'm going all towards ions. That's not saturated. If I'm at the point of saturated, I now have arrows going in both directions. It means I'm exactly at the point where the solid turns into ions, and it's right at the verge of being too much dissolved. Some will start to fall to the bottom, but then there's enough water that it can turn back into ions. And so this is the point of saturated. Right, we're at the point where it can go in both directions. And so when we measure solubility, we are measuring at that point where the maximum ions have been dissolved. The solubility is at this point. Right, because I'm not at solubility if I'm still able to dissolve more. Solubility measures right here where I can't dissolve anymore because I might become super saturated. Questions so far? Okay, good. Okay, so let's look at 2 examples, and then we're going to take a little rabbit trail, and then we'll come back to some more solubility. So let's say I am looking at chloroform and methane. The question is, first, are these 2 molecules both polar, both nonpolar, one of each? Okay, what about carbon tetrachloride? Polar, nonpolar? Have no idea. It would be nonpolar, right? It's symmetrical. What about methane? Also nonpolar, so both nonpolar. So if they're both nonpolar, should they have dispersion forces? Yes, because everybody has dispersion forces. Do they have dipole forces? No, right? There's just no pole. Do they have any hydrogen bonding? Right, so hydrogen bonding has to have an H and an N or an O or an F. Right, so it has the H. So it looks good, but there's no NOF sitting around. So it just has dispersion forces. Both of them just have dispersion forces. The question is, will they mix? Like the video where they do the blender, but it's not quite that. Did anyone ever watch that? Will it blend? It's pretty hilarious. This guy has this gigantic industrial blender, and he throws random things in there, like cell phones, or shoes, or just can the mixer handle it? Just about always yes. So it's just a series of random. It's a guy blending stuff. So the question is, will it blend? And anyway, okay. Well, if you have some free time, like 30 seconds, you can watch that. Will it blend? Doesn't take very long. Like the answer's pretty obvious. All right. So the answer is yes, they mix. Which means they are soluble. Did I tell you which one's the solvent and the solute? No, I didn't. So it could be that I have methane dissolving in carbon tetrachloride. It could be the other. It just means they are soluble in each other. All right, so the question over here, same set of questions. Is sodium chloride polar or nonpolar? Polar, right? This one's polar. What about this? Oh, we already said this one's nonpolar. This one only has dispersion. This one also has dispersion, but what else does it have? Alright, it has dipoles. So will they mix? No mixing. So these are insoluble with each other, which means you cannot calculate a solubility amount for it. Yeah, question. Yep. That would be fine, because technically hydrogen bonding is polar. And to be totally honest, like sodium chloride is actually ionic. It's past dipole all the way to an ion. But for our purposes, it's just dipole. Alright, so it's time to take a rabbit trail, then we'll come back to some more solubility. So if you have a calculator, go ahead and fish it out. Because we're going to talk about how do we know how much solute is in your solution. So in order to determine the solubility, right, we need to know how much solute is in there. We do that using what we call concentration. So there's several ways we can determine concentration. The first one you've probably seen, right, hopefully recently, right, molarity, where this is moles per liter. Specifically, it's moles of the thing that's being dissolved and liters of the thing that's doing the dissolving. Right, so moles of solute. So if I'm saying it's a 0.5 molar sodium chloride solution, in words, I'm saying it's 0.5 moles of sodium chloride per 1 liter of water. Right, those are all kind of interchangeable. The issue when using molarity is that it doesn't tell you exactly how much water to use. So thinking back to your last Gen Chem lab, right, you had the little volumetric flasks. They got to look like this-ish, right, and they have that line right there at the top. And so when you're making solutions, you would dump in the solid and then add water to the line. Do you have any idea exactly how much water you're adding? Not really, you just add to the line. Right, so it could have been you added, if this is a 10 mil flask, maybe you added 8 mils, maybe it was like 9.2 mils. It definitely wasn't 10, right, because you had some stuff on the bottom that you were trying to dissolve. So the issue when we use molarity is that it doesn't tell me exactly how much solution or solvent to use. Which is why sometimes we use molality, which is given the abbreviation little m, to be confused with all the other little m's you have. But molality is moles of solute divided by the mass of the solvent. Right, and so these are not interchangeable because this is telling me what volume. This is using a mass. And so this is a much more exact way to measure how much is in there. So, let's see what I have in this slide. I do. Alright, let's do some of these examples. Alright, so I'm assuming you guys all can do molarity. Okay, so we're going to practice some molality. Alright, so let's say I have a potassium chromate solution. And I don't know what it is, but I do know, I don't know under what circumstances you wouldn't know the molality, but you know how you made it. But let's say that was the issue. I know that I put in 38.3 grams of potassium dichromate and I've used 1 kilogram of water. I want to know the molality. Alright, so this is our warm-up question. There's not a lot involved with it. So how would I go about figuring out the moles of solvent? Use the molar mass, right? So I had really kind of a two-parter. I have to figure out the moles first. Alright, so I have that many grams of it. And it's 19, oh, that's clearly not right. It's not 19.4, it has to be, got the 4, sorry, 194.4. 19.4, crazy. Alright, so it should be the molar mass is 194.4 grams per mole. So do I put the 194.4 on the top or on the bottom of my fraction? Bottom, right, but it's down here. Let's see, so how many significant figures do I get in my final answer? 3, so it should be 0.197. Alright, so now I'm ready to solve the molality of the solution. I use that as my mole. And then because I was feeling generous for the first one, I just went ahead and told you that I already weighed out a kilogram of solvent. And the math is pretty straightforward, so that'll be a 0.197 molal solution. Good? Ready for the challenging one? Okay. I would like to calculate the molality of a 1 liter of 1.22 molar sucrose solution. So I'm in molar, and I want to convert to molal. We know the molecular weight, we know the density. So again, right, molality is moles of solute over kilograms solvent. So in the problem, what kind of molecule is the solute? The sucrose, right? The sucrose is the solute, so I'm going to be looking for moles of that. And then it's generic, so we're just looking for, it's probably going to be water, is the solvent. So the first thing I need to figure out is a multiple step one. Let's see, maybe I'll make some mistakes in here. Moles of sucrose, right? So I definitely need moles for up here. And they told me it was a 1.22 moles per liter solution. And how many liters did I give you? Try to be easy. 1, right? I gave you 1 liter of it. So how many moles of sucrose should be in there? Alright, 1.22. Now the tricky part. Most of the parts. Alright, so I want to know kilograms of just the water. Right? Just the solvent. And I know I have a liter of it. But if you're thinking back to when I made Kool-Aid, right? Some of the mass of my solution is going to be the sugar. Some of the mass is going to be the water. We have to come up with a method to figure out how much mass the whole thing is, and then figure out how much mass just the sugar is. Alright, so let's do the sugar part first. If I know I have 1.22 moles of sucrose in there, how do I figure out how many grams that is? Use the molar mass, right? So just like we did before. Alright, so if I have 1.22 times 342.3 Alright, so I know I have 418 grams of sucrose in there. Are grams the units I'm going to want to use for my math? Probably not. What do I need to be in? Kilograms, alright. So, let's see, divide that by 1,000. Alright, so I know I have 0.418 kilograms of sucrose in there. We're going to put that aside for a second. We'll come back to it. I know I have a liter of solution, but I need to know how much the whole solution weighs. What piece of information did I give you that you can use to start solving that? The density, right? So the density is 1.12 grams per milliliter. How many milliliters of solution do I have? Alright, I have 1,000 milliliters. What units would I end up with if I stopped right there? Grams. What units do I want to be in? Kilograms. I'm going to go ahead and just do it all at once. So is that 1,000 times 1.12? Alright, we're real close to the answer. Alright, so, looking back at my molality, I have moles of solute, right? Done, that's right there. I want kilograms of solvent. I have this. Is that the same thing as just solvent by itself? No, how do I get the mass of just the solvent? Subtract out the sugar. Yep. Alright, so the mass of the solvent by itself is 0.702 kilograms. Now, step 5. Finally ready to solve it. The molality is going to be this many moles divided by this mass. 1.22. So my original calculation was 1.22 molar, meaning moles per liter. But by definition, these can't be the same numbers, right? Because this takes into account exactly how much solvent I used. And this is kind of an approximation as to how much. But ballpark in the same range. Yeah, just little m. Molality, yeah. Yeah, or little m. You might want to spell it out because there's a lot of other m's in there. So if you're trying to keep track, you may want to actually spell out molality. Not to be confused with mass or moles or some of the other m's we're going to encounter. How do you feel about that? Good? Alright, let's talk about some other ways of calculating concentrations. We'll do a flashback all the way back to mole fractions, like we did in gas laws. Alright, so a mole fraction would be the moles I'm interested in divided by all the moles in the entire system. So a mole fraction of A would be moles of A, and then moles of A plus moles of B plus moles of C plus moles of D plus whatever else I have in there. What would be the unit for the top part of my fraction? What would be the unit for the bottom part? Moles also. So what sort of unit should mole fraction have? No unit. right? The moles have canceled out. So mole fraction, this will be the one time that I'm like, please no units. You won't hear me say that very often. But mole fractions do not have units, right? Because a fraction, it's a ratio of two things. And so as long as those two things have the same units, they cancel out. So mole fractions are unitless. Alright, so let's go ahead and practice using mole fractions. Very exciting. Let's say... Alright, we'll do the super easy one first. Alright, so let's say I have a solution that is 1 mole of ethanol divided by 9 moles of water. I want to find the mole fraction of ethanol, and I want to find the mole fraction of water. So looking at the mole fraction of ethanol, right, so I use the 1 mole on top. How many moles do I have on the denominator? 10, right? Without doing any math, what should the mole fraction of the water part be? Okay, what do all fractions have to add up to? 1. So if I know one of my mole fractions is 0.1, the other one must be 0.9, which you could prove. Alright, so that was my super easy warm-up. Probably even have to use a calculator. Okay. Alright, let's do a trickier one. I think you guys are ready for it. Alright, so let's say I consider a solution that I have 28 grams of potassium chloride with a molar weight of 74 and 225 grams of water with a molar weight of 18. I want to find out what the mole fraction of the potassium chloride is. What do I need to do to get started? I need to find the moles of each. Alright, so let's look at the moles of potassium chloride. I'm messing with my sig figs. I'll say 74.0. I'll let you on 2 sig figs. That's funky. Stopping and looking at that, which one do you think is probably the solute? Which one's being dissolved in what? You know, the KCl is being dissolved in the water, right? Because it's at least in the moles. So it is the minority part that's being dissolved in water. Alright, so if I want to know the X KCl, I put the moles of KCl divided by all the possible moles. Okay. If I then ask the follow-up the mole fraction of water, how do we go about figuring out that? where I subtract from 1. Good. That was probably review. Hopefully review. Vaguely familiar. Alright, I got one more way to figure out concentrations. Probably thinking, man, it's way more ways than I thought there was. The last one we're going to consider is something called mass percent. And as the name indicates, right, it is a percent of the whole based on mass. And it is a common way of figuring out, like, stuff you buy in the supermarket. When it's listed, the ingredients are listed. It's usually mass percent, like whichever one is in the greatest amount is listed first, and then it decreases to the very end where that's the least mass percent thing in there. Fun fact, you go check out your cereal, usually like sugar, number 1, then down towards the end, like the colors, whatnot. Alright, so mass percent is the mass of the component you're interested in divided by the mass of all the components times 100% because it's percentage. Let's see, which one did I go with? Okay, we'll do this one. Let's do a practice problem looking at mass percent. Let's say I have an alcohol water mixture and I made it by dissolving 46.1 grams of ethanol into 116.2 grams of water. I want to figure out the mass percent of ethanol, which would be then the mass of the ethanol divided by the total mass. So again, thought we start off with the easy one. I already told you that this is 46.1 grams. And then to figure out the total mass, right, you do 46.1 plus 116.2. See what it's done. Alright, so that'd be like the simplest, easiest kind of question to try and solve. We got time to do the trickier one. No, I'll save that. Trying to decide if that clock is right or not. Oh, it is right. Okay, we got time. Here we go. It's because like this, like there's this practice problem, and then it's like the perfect cutoff for Friday, where we're going to talk about how does temperature play into this, and pressure, and ionic strength. A bunch of other fascinating facts, like when you warm up your soda from cold to warm, what happens to the number of bubbles, right? When it's cold, it doesn't bubble a lot. When it comes to the room temperature, it's gone flat. It's because you've increased the temperature, the solubility of the carbon dioxide has escaped. How exciting is that? We'll talk about that on Friday. Let's do the practice problem. Alright, so the last practice problem. Let's have 85%. There we go. I'll get a hang of this eventually. Alright, so let's say I have an 85% phosphoric acid solution that has a known density of 1.689 grams per cubic centimeter. I am trying to use it for lab, and I need to know what the molarity is so I can make my solutions from it. So the trick to these questions is going to be assume you have a liter of it. Alright, so molarity again is moles per 1 liter. So I'm just going to assume I have a liter of it. I need to figure out how many moles I have of it. The first step is going to be using this density. I can figure out how much the whole solution weighs. Alright, that's a good first step. Alright, find the mass of the whole solution. Cubic centimeters is also known as what other unit? Right, milliliters. So assuming I have a liter of it, since this is percent by mass, I know 85% of the solution is the thing I want. And now I know the mass of the whole solution. So how do I figure out the mass of just the H3PO4? So if 85% by mass is the thing I want, I know how much the whole thing weighs. Let's see, that should turn out to be 14.8. Then it must be that 1,436 grams, 1,436 grams is just the phosphoric acid. What last piece of information do you need to know in order to get from these grams to those moles? Yeah, molar mass and molecular weight. Let's do it then. 1436 divided by 9%. And since we assumed 1 liter at the beginning, it's going to be that number you just found. Very exciting. So now you're ready to do the mastering homework for Friday and for next Wednesday. Because next Wednesday is Chapter 12 homework, and you're already ready for this. Alright, so when you come back on Friday, we're going to talk about how does temperature play a role, and how does pressure, and ions, and all kinds of other very exciting things.